probability. So the solution that is typically used in information theory. Information is so the situation for continuous distribution is analogous. So this is take the discrete case. Sometimes even though it is a PDF, this is empirical, so we still use the summation to replace the integration. Okay. Yeah. So this is only for your personal reading. Then we're back to ours. Okay. So the D of X is discriminator's estimate of the probability that real data instance X is real. So it is a extremely expected probability dx of that is equal to 1, discriminator, and this is going to be output. Or fixed match. This is the fixed max, and then it just this one. So we talk about this later. Don't worry, just finish up this. So then is it real the discriminator of the G of Z is the discriminator estimate of the probability that a fake instance, this is generate instance, is real. So it expected the D of G is equal to 0 since the generating image is a fake. It's not a real one. So the max VD is equivalent, the maximization of the VD is equivalent training the discriminator. The DX equal to 1 and the D of the G generated, the generated image equal to 0. This is a major objective. So there is a two loss function at the top up together. So these two are jointly optimized during the training. So the cycle again, we added one additional loss function into the objective function. Yeah. So on the generator side, its objective function wants to model to generate image with the highest possible value of the D of X for the discriminator. So this is like it's like a C. Which I will try to confuse the discriminator. I try to fool the discriminator. So this is a VG and expected value. If the Z follow the prior distribution, take the 1, the discriminator equal to 1 or 0. And then, so optimize G, that can fool the discriminator the most as possible. Right? And so we expected, so always take an expectation. So it is a probabilistic since we use the fifth, so later. So how can you determine this a 1 or 0? Based upon the image, it can be it can be decomposed into the patches. Patch cake. Into the patches. And by pixel-wise, perform we conduct the subtraction from pixel to pixel, and to evaluate the mean square error. If the lower you set out some threshold, and then for each path there's a return 0 or 1. We just sum them up as an indicator for the entire image. So when the generator is well trained, so generator go close to the input, the original input image as X. So train the generator so that the discriminator is so this is generated in the discriminator close to 1. That is to say, you can set up the 1 minus dg, and this is 1 minus 1. It should be close to 0. If it's less than the 10 raised to the power minus 6, that will be good enough. So this is a this is a precision of the floating point, and thus take log of the torrents equal to the minus 6. Minus 6. Let's try to minimize that. So you can see that if there's a small and then there's a minus 6, we try to minimize as small as possible. That means the precision, to put the precision into the push to the boundary as can be. Then you get it? This is why we take the log, and this is minus, so that's why we take the minimize of the generator and let them as a maximum negative as possible. So we often define GAN as a minimax. This is a minimax gain, which the G wants to minimize the D, the generator, while the D wants to maximize. So you can see that there's a mini-max program. Some mathematical program. It's like a gain theory in the IE. Okay, so the discriminator, generator, and expected value, this is like this. So first of all, we like to maximize. So we try to test the real x, the real image as the true, and push to 1. However, for the generator, and we try to minimize. So the log, so equivalent to training, that is a minimize. Okay. So this is dg, and this is part. This is part. So d of x is the discriminate. So we have done this. So this is the same. The dx of the discriminate estimate the probability density function of the real value. And the EX, right here, EX, is expected value over the real data. So how can we do the exploitation? So this is the image. So from the row to row, column to column, then we take the, so expected value in the discrete manner, we just compute the value times the probability, the likelihood, and then take the summation. So this is expected value. So yeah, let me refresh to give me a little bit recapitulation. Well, so what is expected value of x? Eugene, what do you think? So what is the formal definition of the expected value? Right? So x is a random variable, within that is the x, right? This is the value of a random variable times is f of x is a kind of like a likelihood. And belong to omega. So what is the omega? We call it sample space. Right? So most of application in deep learning is deal with the number or temporal data or image. So it's just a use kind of idea. So then probability phase instances, okay. So discriminators estimate of the probability that phase instance is real. So proves that expected DOG since the generator is the phase. Okay. So EZ is right here. EZ. Expected value all over the random input to the generator. In fact, the expected value all over the generator instant G of G. And so actually this is the generator, this is the discriminator. Yeah, sometimes we just maximize and also try to minimize at the same time. Just like a looping. Every time we use a backpropagation to find those parameters and optimize these two objective functions at the same time. That's quite a clever idea. Yeah, take a look at the flow. So this is let me say that, yeah, it could be uniform. It could be uniform. This is a uniform distribution, -1. So why we put this right here, -1 and 1, since the center at 0, there's a normally distributed noise, and into that the generator, like a diffusion model. So what is the input for diffusion model? This noise. Noise, always a noise. Then use a neural network, the layer by layer, to just a deezer and perform the downsampling and the upsampling. Finally, just reduce to the error. Then we do the reverse reverse processing from the noise back to the original image. So let me see that. This is the same. So that's how take the summation. Yeah, the discriminator totally cost. We use the objective function as an evaluation measure. Then yeah, let me see that. So the generate data, the negative or max, we put the negative, turn the max into we just factor out minus and minimize the minimization, the change to the maximization. So gain, the generator G is optimal when the probability distribution function of the real image is same as the probability of this is the generate of z's. One is the x, the generate is the z of the synthesized image. g of z from the generator. So discriminator can be obtained. Yeah, this is a p. This is the discriminator of the y. This is the probability of the original data, and this is generate, and this is the probability distribution of generate function. Then so take this ratio if let me say that the d if they are close to that, and then if this is a real one and this is so this is going to be if we input the real data, and then so this term going to be 0. So the p data of y divided by y is equal to 1. Then if your input is a fake, and then the g of z and the probability, so this number will close to 0. So use this kind of ratio to adopt it as a threshold to determine what kind of value you're going to use for training. So the optimal discriminator predict is 0.5 for all the sample drawn from the y and g of x. So this equivalent to say that the generator g is optimal when the discriminator cannot distinguish between the true and the generator. Yes, this is 1, this is 1, and 1. So this is like a balance between the generation and discriminator, right? So, so the discriminator should close to, so for the real data is close to 1. So this is the probability data of the y is equal to 1 and z equal to 0, given that. So this if finally we reach the equilibrium 1, 1, 1, it should be close to the 0.5. Okay, then the optimal condition is achieved. Yeah, this is something we would like to express. The generator try to make the discriminator d. Predict dy is a 0.5 and the d of the g of x is a 0.5 as well. So the objective function of the gain can be expected into that. So this is the gain. This is the loss of the gain function. So this is the minimax we already mentioned. Input the discriminator generator. This is the prior distribution d, and 1 minus d, and then so this is generator. So again, train the d in here to max the probability of the assigning correct class to both training class to the training sample once, and synthesize sample from G. So it train the G in here to so those parameters, even though the internet structure is fixed. However, the only thing we try to is the parameter used to construct the generator and the generator and the discriminator. So the G in train such that the G of Z is as close to Y as possible. Then we stop. So however, this is the problem. Simultaneously try to optimize two objective functions. What kind of the risk we have to take? What kind of risk we have to take? Since these two objectives, they are like a conflict of the interest. What kind of situation we're going to face? Collapse. So what is the meaning of collapse? 叫崩溃, right? When you train, finally, it doesn't converge. even though it blow out. Sometimes you look at the conversion plot, even though you spend a lot of the compute capability, it doesn't return a satisfactory model for you. So it happens all the time. It happens all the time. So GM model. So last year, there's so many group of the student cannot provide the conversion results. So it's sometimes. So if you ask me, how can you deal with that? You need to learn some lesson and experience from the people that show their result from the Quora. You ask some question or typing or even typing the ChatGPT that will give some indication what is the possible potential right direction you should proceed with. Okay, so yeah, it's like a cross entropy and turn into the loss function. Let me PC again. Okay. Before I do that, I wish you can just perform the cycle game, and I would like to introduce my paper first, and then we go back to the DC game. This is deconvolution, and this is we also have a W game, Wasserati game, and the style game, then the cycle game. Yeah, W game, to call the W game. Wasserstein generated, and the Wasserstein, and also have C game, conditional game. This is for the anomaly detection. We add a condition on the discriminant for the anomaly detection. You like to do the anomaly detection? How? Since this is the generator, this is discriminator. They're going to turn out the indicator, the image is true or false, 0 and 1. You use a discriminant. 1 to 1, the DNG has been trained well trained. The ratio close to the 0.1. You have a quite potential capability to differentiate what is a true, what is a false, and the train and the inspector instance just went through all the generator and discriminator directly look at the output as an indicator, as a fault detection or anomaly detection, right? Serve as serving as one class. The one class model. We only train all the. We just use the one class model. Once any deviates, so you're going to signal. As long as the model will not. So the model. So there's some presumption. If the model can be well trained, otherwise, so the anomaly detection is going to be terrible. Most of anomaly detection, the accuracy, the upper bound for the one class model about 80%. The 80%. A lot of false alarm. The false positive instance. Now this is something we cannot deny. Always we have to tolerate the false positive rate. Really high false positive. Okay, go back to here, and I will elaborate later. Let me go through very quickly. Yeah, this pixel to pixel model, unit. Okay, the finally try to identify and to expose the edge as clearly as possible. Then cycle secant. Yeah, cycle gain. So we move to the cycle gain. That okay, please just download the paper I share in the line group, please. Just we go through it and step by step. Very fun. Yeah, look at the user cycle gain generated adversarial network temporal row trace data. So what is the meaning of the temporal? It's time dependent. It's like a time series. It's row trace data. Augmentation. Why do we need to perform the augmentation? Augmentation, that means we need more data of that particular process for fault detection for the FTC. Okay, so be sure, please be sure we will return to the slide, talk about the C gain and the W gain and style gain later. So rest assured, I'm going to review every one of them. Okay, so for this, why we need to do this research, the objective and the research aim is try to improve the performance of the fault detection. So typically, what kind of methodology are used for fault detection? Chen-Yuan, what do you think? So what kind of the tool of the fault detection are utilized? Typically, if you were the process engineer, what would you like to use?
SBC.
Yeah, this is one of the most frequently used. Before the era of the machine learning, they use the SPC, the upper bound, and the upper control limit, center line, and the lower control limit. If any point just extrapolate the upper bound or smaller than the lower control limit, and the signal is issued, that signal will send to the process engineer. Then whenever she or he receive it, they just check everything, check the machine, check the method, check the raw material, check everything, and to make sure everything is okay before the operation can bring it back, can bring the operation back into into the condition. So, yeah, good. Anything else? Zhihen. FTC, fault detection and classification. What do you think? Fault detection? And Ninja. Or Guanjuan, what do you think?
Improve the product's quality.
No, I mean what? In order to achieve the fault detection purposes, what kind of tool can be utilized?
AOI.
Yeah, AOI. This is a fault detection. However, AOI is take the image, and how can you identify the defective image? What do you think?
Yeah, the original is compared.
Yes. Okay.
Okay.
So even though you do the image subtraction, right? So So yeah, it can be. So it can be considered computer vision. Perform the image subtraction. This is normal. This is the inspected, the subtracted. It should be 100 identical. If this is subtraction 0, 0, so all the image subtracted image should be totally black. Am I correct? Right? Like this. Subtraction. Yeah, this is pixel to pixel. So this is we call the template. So mean that this instant under inspection, inspected. So this minus this, so this minus this. If they are identical, so 3 minus 3 is 0. So in the 8-bit representation, 0 represents all black. So this minus this totally should be all black. Right? Totally all black. If there's some defect or difference, we're going to show, well, okay, so like this. So this is a little bit different, like this, like this. Like this. They are different. So in here, we're going to show some pattern. There's some pattern right here. This pattern is between the differentiation between the same local area of the two images. Right? Or anything else? We can perform PCA. So what is the PCA? So the process kept a principal component analysis to build up this envelope. It's like an ellipsoid. This is the principal axis, first principal axis, the second principal axis. Construct the confidence band, right? That any point after the pre-PCA transformation going to plot the point within the envelope of mine. If it is right here, then signal is given, is released. Yeah. Called the PCA. Right? It could be two-dimensional, could be higher dimensional. Okay, this is something frequently implement in practice in order to identify the abnormal condition. Hey guys, first of all, detection. This is abnormality. Not normal. This is a not normal, called the abnormality condition within the image or within the process. Something you need to you need to prompt the engineering at the first time, as long as it happened at the right time. Then. So what is the C? What is the C means, Mr. Fu? FDC, for detection and classification. So that is a more profound question being asked. So once what you find, well, this is the differentiation, then this is the question. This question is being asked, this is defective, which is not normal. The next question goes to what kind of root cause for such abnormality, for this defect, for this defective item, for this defective product, called classification. We try to find the root cause. And the root cause can be traced up and upstream to what machine? What kind of tool? tooling can be further traced up to the pipeline. Can you tell me within this tooling what the parameter? Corresponding to such a failure, right? Parameter. And then going forward or traced up upstream to the pipeline. Can you answer my question? What is the corresponding sensor? Sensor corresponding to the temperature, the pressure, or the rotating speed, and so on and so forth. This is some question. There's so many questions need to be answered. So that's combined collected called the MDC. For concept detection, as long as it can be detected, it's known as the detectability. And then please classify what kind of the root cause for such a failure. Okay, question? Then just we're going to do this. So in modern manufacturing, semiconductor manufacturing, the sophisticated process control mechanisms are standard. So since we use extremely gradient boosting, use the SPC, however, this is a class imbalance issue arises. What is the class imbalance? I mean, you only have a small number and a very limited instances of the minority information that is available that can be used to train the model. Like you teach your children how to use the chopstick. I always like this example, like a father or mother will, your child try to learn how to control or master the skill of the chopstick during the dinner time. So you need to practice and practice and practice, right? If the practice period is very short, that means this exercise does not provide enough information to the model. The model is the brain of your boy or your girl. Then she or he cannot handle the chopstick. Yeah. In such a case, so typically this is the population. In the current semiconductors practice, the really high yield, that means most of the output of the wafer production, they are conforming. They are normal wafer. Only very tiny number of the group for the wafer that are defective. So most of them are normal. And the very tiny portion, they are abnormal. Typically, you can see that, like a 7-nano process on this TSMC, or even 4-nano, or even 3-nano technology. The yield is almost over 95%. Okay, let me take an example. Most of the iPhone, what kind of technology has been taken? 7-nano technology. This is almost over the 98% of the yield rate. That means every 100 wafer, only two detected as defective or abnormal. So less than or 2%. So even though, so this is very limited information provided to the model for learning. What's going to happen? What is the consequences? No, they do not learn well. They do not learn well. Why? Since a very limited information about the abnormality, they cannot teach them how to identify. That's called a class imbalance arises. For example, so then the model can, without training, to tell you all the wafer being produced are 100% normal in the normal condition. If make a wild guess like that, so what is the ACC? So what is the ACC? Accuracy 98%, right? 98%. 0.98. And what is the recall? What is the recall? 0. It doesn't even pick up any one of the abnormal or defective wafer. They just make one, okay, pass, let it all go. So it doesn't have the function, it doesn't have the mechanism for the detectability. Even though it's a 0.8, this number is fantastic. It almost convinced the process engineering so we can go on, so it can go live. Then however, recall 0. We don't even pick, we don't even identify any defective wafer in any sense. So this is the issue. Even the ACC accuracy is so high. So this is misleading. So this number is totally misleading. Okay? So then back to here. So one of the major challenges data scientists face is the scarcity of sufficient row trace data. Row trace data for the detected wafer, since it's considered a minority. So the normal is majority. Majority consider positive or negative. Inja. The majority class is considered the positive or negative. Negative, right? Since most of the human beings are not COVID affected, right? So only very small number of the human in society are COVID infected. So they are minority, right? So the minor, abnormal is the minority. So this minority consider the positive or negative? Positive. Positive like that, you go to the hospital for your cancer check. So only for small a portion of the people are cancer affected. So they are called positive, right? So then to address this issue, what kind of issue we are addressing? Class imbalance issue. And this paper proposes a novel data augmentation structure based upon the cycle gain and strategy. So we are using two different strategies. What kind of the way you generate the synthesized data? The second, synthesize the augmentation structure and the strategy utilize cyclogen as an artificial intelligence application to synthesize temporal data, low trace data for diffractive wafer. So we have a different augmentation strategy, we have a different structure strategy. Two strategies will be addressed. So cycle. So one way we input like this. Cyclogen. Okay. So sometimes it is, why is it so appealing? So sometimes in the data set, in the data collected in the ERP system, so many abnormal wafer, so few. So many normal wafer, so few abnormal wafer, like that. And this is horse, and this is zebra. So this is cyclogen. We input a zebra, and then we try to fool the discriminator to produce the horse. This is the first, the upper part of the cyclogen. Second, we input the horse to transform the horse into the zebra. So this is like a cycle. This is a generative adversarial network. Okay, we take a break.